afternoon. Salutations. Welcome. Nice to see you all. Thanks for those of you who are joining us again, who were with us yesterday. And thanks for those of you who are first time with us today. So we're going to go ahead and get started with Keaton's Capstone presentation. Students work on these at least for one semester. Sometimes it's for longer than one semester. We're super duper proud of Keaton. Keaton's mentor is Dr. Greg Trickett. He's been working with Keaton on ontological discourse within quantum philosophy, an investigative glance. Mr. Keaton Barnes.
Thank you. Let's get started. Okay. Introduction. So, to preface, I'm sorry, but you did choose to be here. The goal of this Capstone project was to try and make quantum mechanics and science a little bit more accessible. And so I'll just be covering the relevant basics in accordance to its application in quantum philosophy, or a subsect of quantum philosophy. And I will indulge in the classical ontological argument at the root of quantum philosophy. And to begin, the quantum part of quantum philosophy may seem intimidating, but it just means, small. So the smallest amount of something, especially energy. Let me just tab back over. Okay. The ontology part is also very intimidating for those uninitiated. But it falls under the umbrella of metaphysics, which studies both existence and knowledge. And it's the part of philosophy that studies what it means to exist. So, basic definitions out of the way. Now we can get into the fun stuff. Basic quantum physics. So, how did quantum physics diverge? As a field, it diverged because physics is very deterministic. So you need to select, one of these variables, and you can predict another variable from that. Whereas in quantum physics, you need to predict the chance of that variable being that way. So it's more of you're guessing. But it's an educated guess. So, concrete description of mass are usual physics, and, quantum physics needs to describe multiple distinguished states. Then there's the double slit experiment, which it pretty much describes light behaving as a wave and a particle. This is done through two slits which collide with a back screen. I'll show some pictures here in a second. And there's a decent bit of weirdness with this experiment and the way that light will form a predictable interference pattern, which I will show you. Or actually, maybe I can just... Yeah. Wait, no. What? Hold on. Oh yeah, because I put the observer effect before. My bad. I'll show you here in a second. But light aligns into a predictable interference pattern. It will do this even if it's fired at a single photon at a time. So if you had one little bit of light that just hits one spot, it'll always fall into that pattern, even if it's not interacting with itself. So you'll see. And notably, this is affected by the observer effect, which pretty much just says that if either slit is interacted with, or if either slit is measured, then the photon is disturbed by consequence of the measurement. And that means it'll change its trajectory and conceptually, not much is going on. Obviously, if you fire a electron or, interact with the photon in some way, then it's going to change its trajectory. But yeah, here's the expected results of the double slit experiment, not the actual results. These are the expected. And what it shows is the light beams, radiating out, and you would expect them to align into very distinct spots. However, what actually happens is it interacts with itself and forms multiple separate spots in which light appears. And I mean, it's just supposed to be an example of, the fact that there is some quantum weirdness in where multiple states can interact, or a projected state can occur. Can't really explain that very well. But the measurement problem is a sister concept to the observer effect, which what I mean by that is that it asks why quantum systems, upon observation, must decide one single state among possible many states. Good example is Schrodinger's cat. Obviously, is the cat dead or alive? It's technically, well, to some interpretations, it's both, but that's just a consequence of the field. There are many different interpretations, and there are a single state whenever you actually measure. And then there's quantum entanglement, which is the final concept that I need you guys to learn. So stick with me. So imagine two particles or spheres. One sphere must spin clockwise, and the other must spin counterclockwise. And therefore, anytime you measure the spin of the direction, or the spin direction of one, you necessarily know the other direction. So if one's spinning clockwise, then you know the other one's spinning counterclockwise. And this is typically represented in the form of a wave function. Or, well, no. That's quantum states. I don't know why I put that there. My bad. But as you can see, that's a wave function. You can see how that looks. That's just a representation of probability mapped onto peaks and slopes. And then whenever the wave function collapses, it's one singular spot. So, it's one state. I'm trying. There will be questions after. And then we get into ontological discourse. So there's the Copenhagen interpretation, which is the widely accepted interpretation of quantum physics, or it's just foundational. It was formed by Heisenberg and Bohr, which are both aligned with the ideas of positivism and Kantian thought. And what this means is, positivists believe in a posteriori knowledge, which means that true knowledge can only be gained post or after the fact. So through reason and study and not direct observation, or not direct empirical observation, not something that you experience yourself. Am I okay? Whatever. And Immanuel Kant is obviously the creator of transcendental idealism, which means that the universe, I'm blanking. it means that I'm struggling. It means that there is, you know, the most real part of your experience would be yourself. So your own thoughts, your perception, not the actual reality. And it principally assumes that observation has a very real effect on the state of a microscopic object. And I'll get into why it's not applicable to macroscopic here at the end. But you know, Albert Einstein, he has some opinions. He has celebrity status, so he's had a huge impact on the field of quantum physics simply because he is a notable figure for pretty much everyone. And he's a significant supporter of realism and the fact that, like, stuff must occur despite our observation. And, you know, he accepted the world for what it empirically seemed to be. And a famous quote is, do you really believe the moon isn't there when nobody looks? Like, he was not dealing with Bohr's idea of, you know, quantum states and observation, quantum states being decided upon observation. As a result, he looked at quantum physics in a very critical light. And so he you know, made an argument against it. And this was in the form of the EPR paper, which was not what he was hoping for it to be, because his partners kind of just posted it without him. But it did introduce the EPR paradox, which is you know, very impactful because it's talking about relativity and how light can, you know, nothing can move faster than light, right? So then you can't have this connection between these two particles across long distances that you would get an entanglement. So, for example, if you have this particle way over here and it takes like more than a light year to reach it, and you have this particle way over here, that gap, or you can't transfer the information between those two particles faster than light. So even though you observe this one and you know the other one because of that collapse of the wave function, you can't have that. That's just not something that should exist given relativity. So therefore, there must be hidden variables that are decided at inception of those particles that activate upon observation. And obviously, people weren't going to just take what Einstein said as an absolute fact, and then came across Bell's theorem, which it consists of retorts, which it's multiple retorts to the EPR paradox. And what it describes is that it describes that EPR was very wrong. And this is because what the scientific measured like experiments and stuff ended up being were very separate from what was anticipated with general relativity. It was instead more in line with quantum mechanics, and only gave more support for, an idealist point of view on things. But yeah, so quantum idealism. If Bell's theorem is taken as gospel, the world depends on observation. And this is inherently idealist because your perception is the most real. Your observation is what you have. And one of the many appeals to this idea, is quantum decoherence, which, to put it simply, is just like you are constantly observing your environment, right? So then you are constantly collapsing that wave function of whatever is directly in front of you. And so because that thing directly in front of you is related to all these things that are, across the room from you, that requires that it stay real, pretty much. Which in quantum computing, this is separate. There is a focus on making a coherent environment that is separate from everything else by supercooling it and stuff, and that allows for qubits and stuff like that. But you don't really need to know that at this stage. But yeah, it chains the act of observation and gives stability to reality in this interpretation. But in conclusion, it's inconclusive. So there's significant support for a more idealistic view, but that's not to say that things aren't realistic. You can't really decide that it is how it says it is, or how it seems to be, because it is just such a inconclusive field by consequence of its existence. So don't start thinking nothing matters just because some tiny spheres spin opposite of each other. And I hope you found what I had to say interesting and not psychological torture. And then there's my sources. But yeah. Okay. Any questions?
Yeah. I'm sorry, Keaton, if I gave you an expression that was distracting. Genuinely, I'm sincerely sorry. But I think so. I could be wrong, but I think you, in your explanation of a posteriori knowledge,
Okay.
you I think mixed up a priori and a posteriori, because what you described I think was a priori, meaning a reason.
No, I mean it's because posteriori comes after the fact. Like it's generated through scientific understanding, right?
Yes.
Empirical
Yeah.
observation.
Yeah. Okay. Yeah. So then I just used empirical wrong.
That's
Yeah.
But I'm sorry. I distracted you.
Yeah, you said a line in there. I think what he's talking about, but I think it just got. I just think the way you were saying it got a little.
Yeah, jumbled.
But that's cool.
Okay.
You mentioned quantum decoherence
Yes.
as why it doesn't affect macro.
Yes,
events?
because an environment, it has all these interactions going on, so everything is connected. Therefore, you are observing your environment as it is, as it's connected to one another. So, should I try describing that a bit better? Do you think it's good? Dude, just tell me.
So what I'm trying to figure out is if you had a system that was completely isolated from any other thing, no matter its size, would it become a quantum mechanics problem, or would it still be a macro physics problem?
That's a quantum mechanics problem because you are like talking about a coherent environment, which implies that a superposition is actually able to be held. So a state along that wave function, which I showed you guys, but it shouldn't have been on that entanglement slide. I'm sorry. But yeah.
Size doesn't matter.
I mean, it very much so does.
I was trying to science.
But yeah.
On your slide about Bell's theorem, you had a mention of polarized sunglasses.
Yes.
Being to an example, I'm not sure I picked up.
Yeah.
How do polarized sunglasses?
Okay. So whenever you take two lenses of polarized sunglasses and you lay them across each other, one at a 90-degree angle and one just perfectly, one at a 90-degree angle and then one at a 0, whatever, they cancel out all light. And so you kind of just like, you expect that because it's light entering in one way and then it's light entering in another way. And so it blocks both of those directions. But if you were to take a third lens, then you would actually see more light in between those two lenses. And that's not really something that's accounted for by regular physics. And minute physics, as I like showed very briefly there, whoops, that's not what I wanted. Hold on, dude. I really should have just done duplicate screen. Let me just find it real quick. Yeah, minute physics is what I used, which I actually do have the tab pulled up. This right here. So you can actually kind of see what I'm talking about, where it's darker, but on the third overlap, it's visibly brighter, and that's just because of quantum physics and how it interacts with that. Which yeah. Okay, more questions.
Well, I just
Nichols.
want to know, why did you choose this topic? What led you to?
I wanted to force myself to learn it. That's really the main idea, and I have gotten a lot of exposure through this, like much more than I would have if I didn't, do the project, because I need to find a way to motivate myself. And then trigger.
So what are the implications, real world implications, if idealism is true? So your conclusion was it's indeterminate. Say that it is though. What are the real world implications here?
Well, it's not like it would definitely be a softer idealism, right? Because you would still have reality. It's just that, it does depend on a lot on perception, but also, I don't know, like, because it would imply that reality can change simply based off of what you think or what you perceive, which.
Well, at least off of your subjective perception, right?
Maybe yeah.
What you randomly think, but what you perceive, yeah.
Yeah.
I have an inclination that not much would change.
Yeah.
Right, if it were true, because if it were true, it would have been true all along, right?
Yeah, it wouldn't have changed.
Right. So here's my other question. Is idealism necessarily not realist? You kind of seem to imply that idealism is not real. Is not real, or a view of the world that implies the world isn't real, right?
I think it implies that the states don't exist Okay, so I think quantum states, right? It implies that they cannot, okay, hold on. Let me put together my thought. So realism implies that these states are already determined. They are determined whenever they're created. It's just like a hidden variable that's decided. And that is something that will occur even without you looking. That's just how the universe, would even be assumed to work. And then an idealist interpretation would imply that, everything relies on the act of observation, and that is just not how the universe works. Like that, you can't have these, I guess, you can't have stuff already be decided. It has to decide at point of observation. So that's the difference between the two. They can't overlap. Yeah. Any more questions? How about reviews? Okay.
Not really a question, just more like a anecdotal question for you. So these are like two very massive, thick subjects to try and like have talk to each other.
That is why I put investigative glance. Like.
So what was that like having to kind of dabble in both of those worlds and try to make them talk? Because I don't know anything about quantum physics or anything like that, but from my understanding, it's still pretty subjective and new.
What's comforting is that a lot of quantum physicists and people like that, they also have no idea what's going on in quantum physics.
Yes. So with that being said, with ontology, right? Ontology is a pretty foundational thing
Yeah.
in philosophy. How do you not warp what ontology says to fit quantum physics then? Like, do you find that you have to change things within like the philosophy side in order to look at the science side more?
So are you asking like if it's, or if the science is dependent on philosophy, or the other way around?
Yeah, I think that's how do they talk to each other, I guess, doing your research?
I feel like there is a distinction between like the implications of the ideas and the ideas themselves.
Absolutely.
So, you'll have these people that dabble in both fields and then can kind of explore the implications of these ideas, but then you'll also just have the physicists, and they don't really, I'm sure they do it or they think about it just for fun, but it's not really part of their ideas.
For like two experts in their respective fields to have a pretty good conversation with each other.
Yeah, for sure.
Or for one individual to be an expert in two different fields.
Mm-hmm.
Your list, there are quite a few people who are doing work in this. It's not like,
Yeah.
to kind of answer, it's not like, this was great, by the way. I didn't start off, you did a really good job, first off. But it's not like you did this and nobody's ever done it before. Right?
Yeah.
There's plenty of people working at the intersection of philosophy.
There's a lot of resources. Because it is indeterminism is inherently philosophical, and how the world works, how reality is also inherently philosophical. So it's they overlap. Yeah. Did you say they're dating?
So I guess one of the implications I was trying to kind of tease out of you a minute ago, and you pointed to it just now, is do you think that there's any implication for what you're doing here with something like free will?
Yeah. Because things are in a quantum state inherently, you can have free will because it's indeterminate, and that's something that I find kind of beautiful about quantum physics.
Can you say that sentence one more time? I didn't hear if you said can or can't.
Uh,
Can you say that sentence? Because
Okay.
everything is inherently in a quantum state.
yes,
You can or can't. I just didn't hear you. Have free will.
you can.
Can't.
Yeah, because it's indeterminate. But yeah. Any other?
Would idealism change that though? I think this is what I was trying to get at before.
I mean, I feel like it doesn't affect your choice if reality is idealist. It just changes how reality is. Like, those are separate in my idea.
Very good, thank you.
All right, Keaton.
Yeah, thank you.